So let's talk a little bit about some extensions of linear connection over a given manifold M. The extension we want to give is actually will turn out to be a derivation of vector fields over M tangent along a given smooth function defined between two differentiable manifolds. So first of all, what is a vector field defined over M? Tangent along a given smooth function f. So let f be a function from M to N, two smooth manifolds. A vector field x is said to be defined over M and tangent along f if f is equal to pi composite x. Nothing more than this. Very, very easy. Now, we want actually to obtain a derivation. Let's call this derivation, for the sake of completeness, delta bar, which will turn out to be a map from key times key fm being the space of fields of M tangent along f, into key fm. Well, we must give a meaning to this kind of quantity, delta bar v of x, where v is a vector of Tpn, and x is such a vector field defined over M tangent to f. First of all, there's a natural map ρ, which maps vector fields of M, so key M into key fm, defined as follows: if y is a vector field in key M, then we can define y of fp equal to y of p, and y will turn out to be a vector field of key fm. So to give a meaning to delta bar vx, what we can do, first of all, we would like to have a nice property, which is the following: let A be a map from N into the reals. Then we want that delta bar v of ax is equal to a delta bar v of x plus v of a x computed in fp. This is natural, but we still have to give a meaning to delta bar v of x. How can we do this? For example, assume that x is equal to rho of y being an element of key M. We would like that delta of, obviously, for example, we can set w equal to the differential of f computed in v. We would like that delta bar v of x should be equal to delta of the differential of f computed in v of y. So delta w of y. Now the construction uses local coordinates and whatever, and so over. So the first thing we can do is to pick up a point P of n and the corresponding point f of P in M, choose an open neighborhood U phi of E of P and an open neighborhood W psi of Fp. First thing first, it's a construction, uses local coordinates. So what we can do else? For example, to each vector field x of key fm, we can associate naturally a vector field x prime defined as the differential of psi computed in x composed with phi to the minus 1. This is another vector field. Actually, if we set phi of u equal y prime and psi of w equal w prime, this vector field is tangent along the map G equal to psi composite f composite phi to the minus 1. This is the now what we can do else. Psi minus 1 G. We can for example we can try okay, now the connection delta defined over M naturally give rise to the connection delta prime over u prime over w prime, sorry, over w prime. This is actually a straightforward fact that a connection over a manifold give rise to another connection over the real space which gives the coordinate to the manifold in question. So this is step forward. This means that if we can define, for example, let's call v prime equal to the differential of phi computed in v and w prime the differential of psi computed in w. This means that if we can define delta prime of v prime x prime and we call it zeta, we can come back using the map psi to the minus 1 to define the vector field d psi minus 1 of zeta. And this vector field is all we need to define the connection, which is a derivation of vector fields over M defined over tangent along F. This is all we need. So we must give a meaning to d prime v prime x prime. How can we do this? For example, G has got simple coordinate. For example, f of p is equal to x1 of p, xn of p, and psi of fp is equal to y1 of fp, ym of fp. Then G can be written easily as y1 x1 xn dot 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 ym x1 xn. This is the coordination. So vector field x prime, which is defined over M and tangent along F, has got in coordinates a very easy form, which is the sum over k of a k of x partial derivative with respect to yi or yk. This means that when we apply the connection d prime to this vector, we obtain basically the following thing: summation over k of a k delta prime of derivative with respect to y prime plus v prime applied to a summation over k, obviously, derivative with respect to yk. Now we already, but it's actually easier in this way because derivative with respect to yi are global fields, and this step forward to see that rho of derivative with respect to yi is equal to derivative with respect to yi. So the delta prime of v prime of derivative with respect to y prime must be equal to the derivative to the delta of the differential of g computed in v prime of derivative with respect to y prime. This is because we want this property to hold. So we obtain a linear connection delta prime, and by using psi to minus 1 a linear connection, a derivation of the fields over M defined along F, tangent along F, which satisfies the properties of linear connections. Very, very easy. Now, this construction is very important when we consider n to be an interval of the real line. In this case, the map F must turn out to be a gamma, which is a curve over M, and we can define delta of the derivative with respect to t of x. Here x are actually vector fields of M parallel tangent along gamma, and they actually are written as the sum over k of a t derivative with respect to xk. So we obtain that this thing has got is a very good looking system of equations in the variable x xi, and yes, basically is written in terms of the connection coefficients. So it's a system of differential equation in the variable x xi of t. Xi of t, where obviously xy of t are the components of the vector field xi are the components of the vector field defined over M tangent along gamma. Now we say that now let M be a smooth manifold delta, a connection over M over M, and assume that gamma from J into M is a smooth curve. We say that the vector field X is parallel along gamma if the delta of derivative with respect to t of x is equal 0. So the notion of parallelism is implemented also on manifolds by using linear connections. Now, this is a system of differential equation of first order, so a linear system, which means that the space of solution is a linear vector space whose dimension can be proven to be equal to the dimension of the manifold M. Furthermore, for each initial value there exists one and only one solution from Cauchy theorem on existence and uniqueness of solution for system of differential equations. And we can build linear isomorphism. For example, let J prime be a subset of J prime, and assume that Vj prime is the set of the vector space of vector fields parallel along the restriction of gamma to J prime. We can construct the linear isomorphism ρ s for each s belonging to J prime as a map which goes from Vj prime into T gamma s of M. Define it as follows: ρ of x is equal to x of gamma s, x computed in gamma s. There's another linear isomorphism called parallel transports, which can be built as follows: tau sw is a map from T gamma S M into T gamma zeta M, and is defined as follows: tau of S zeta is actually equal to rho zeta composed with rho minus 1 of S. This is the parallel transport. It's a linear isomorphism. So we have a theorem. If Jm is a curve over M, smooth curve, if V gamma is the set of vector fields parallel along gamma, then the dimension of V gamma is equal to the dimension of the manifold basis manifold M. There is a linear isomorphism ρ s for each s belonging to J, defined as ρ x equal x gamma s, with rho is obviously from V gamma into T gamma s M. the parallel transport tau S zeta defined as rho of zeta times rho minus 1 of S, which is a map from T gamma S M into T gamma zeta M, is a linear isomorphism. The vector field Vt defined as tau St of V, V being an element of T gamma Sm, is a vector field parallel along gamma, so delta derivative with respect to T of V dt is equal to 0. This holds for each S and T belonging to J, and in the end we have that tau of Ss is the identity of T gamma Sm. Tau S zeta is equal to tau zeta S minus 1. Tau SW composite tau W zeta is equal to tau S zeta, and this holds for each S, zeta, and W belonging to J. Last thing we want to talk about today is the notion of curvature tensor. So given a manifold M, given a connection, linear connection delta on this manifold, and let K be the set of smooth vector fields of M. Then a curvature tensor is a map R from Km times Km times Km into Km, defined as delta x, delta y, zeta, or R of x, y, zeta is delta x, delta y, zeta, plus delta y, delta x, zeta, minus delta of the commutator of x and y, zeta. This is the curvature tensor. Now, the curvature tensor is antisymmetric in the first two indices, is obviously linear with respect to C infinity function, smooth function, real valued smooth functions. So for example, R of f x g y h zeta is equal to f g h r of x y zeta, where f g and h are in C infinity of M. Moreover, it has got a punctual nature. For example, if W is a vector field such that W computed in P is equal to 0, then R of x, y, W computed in P is equal to R of x, W, y computed in P equal to R of W, x, y computed in P equal to 0. And moreover, if x, y, and zeta and x prime, y prime, zeta prime are vector fields such that x p is equal to x prime p, y p is equal to y prime p, zeta p is equal to zeta prime p, then we have that R of x, y, zeta computed in P is equal to R of x prime, y prime, zeta prime computed in P. So it has got a punctual nature. Now, a tensor of type Rs is a smooth section of the bundle T product S of M times T star product R of M. A tensor of type 1S is a multilinear map which goes from key Sm into key, such that this is a map K, such as it is punctual. For example, if xi of P, so xi computed in P is equal to 0, then K of dot 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 xi dot 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 closed parenthesis computed in P is equal 0, and moreover it's linear with respect to C infinity function. So if f is in C is a smooth function, real valued smooth function, then K of dot 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 f of x dot 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 is equal to fk dot 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 x dot dot dot. Now the curvature tensor is a tensor of type 1-3. It has got also very astonishing form in coordinates using coefficient symbol, connection coefficients, and so on. And last thing, the torsion tensor. Torsion tensor is a tensor of type 1-2. So it's going from key m times key m into key m, defined as t of xy is equal to the delta xy minus delta yx minus the commutator of x and y.